So what is this course about? The other half of that is data. Computers need both algorithms and data to solve problems. Without the algorithms, you couldn't actually do the problem, but without the data, you're not solving any problem worth solving. Data, being able to process a lot of data quickly is how computers are useful, being able to store lots of data and do things with them. Taking tasks that would take a human being a long time and making them happen really quickly. And put simply, data is just information. In a computer, all that information has to be stored either in active memory or long-term storage. So, one of the primary ways computers store information is tiny switches in active memory that are either open or closed. So they can be zeros or ones. A lot of long-term storage media uses different optical or magnetic and different possible ways, but you can think of it as zeros or ones. Everything's got two states, and we can abstract it by representing information with zeros and ones. So our number system is base 10 or decimal. That means we have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And our place values are powers of 10. So 234 is 2 hundreds, 3 tens, and 4 ones. The number 23.15 is 2 in the tens place, 3 in the ones place, 1 in the tenths place, and 5 in the hundreds place. So it's 23 and a tenth and 5 hundredths. And you guys all know this. This is stuff that you learned in elementary school. But with binary numbers, we're representing with numbers that are base 2. So we have 2 to the 0, 2 to the 1, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. So our place values are 1, 2, 4, 8, 16, 32, right? So if we go back here at this slide, in decimal, 0 and binary 0 are the same. 1 is the same because the 1 means that. But in 2, for decimal, in binary, there is no 2 digits, so we have to have 2 in the 2's place and 0 in the 1's place, so 1, 0. 3 is 1, 1, 4 is 1, 0, 0, 5 is 1, 0, 1, 6 is 1, 1, 0, 7 is 1, 1, 1. This pattern that you see, it's the same pattern you see with decimals, right? In the next one after 9 is 1, 0. It's 1 in the tens place and 0 ones. And after 99, it's 1, 0, 0. Because you get to the highest two-digit number, you go to a 3-digit number. And that's what happens with binary. But we're going to spend some time with binary numbers next week, practicing a little bit so you understand how they work. But I just want to introduce this idea here. Now, decimals work the same as numbers less than 1, which we call decimal numbers in decimal, but the binary numbers, place value to the right of the binary point, are just the 1/2's place, the 1/4's place, the 1/8's place, just like it's the 1/10's place, the 100th's place, the 1000th's place. So it should be pretty easy to see that we can represent numbers in binary or decimal. Like I said, we'll practice binary numbers some over the next few weeks, so you'll get more comfortable using them. Right now, it's just the whole idea of that it should be obvious that we can represent numbers with numbers at just different base. Now we come into the thing, aside from numbers, sometimes we want text, right? We want characters. Well, you can represent the integer 131 as a binary number, but how do you represent the name Bob as ones and zeros? That's not as obvious, right? It turns out what we use is we create a table that allows us to convert each character into a unique 8-digit binary number. So a collection of 8 bits is called a byte, and that's a basic unit of computer memory. Every character can be represented using 1 byte of memory. And the code we use is called American Standard Code for Information Interchange. And there's a table. I actually have a link to that on Schoology. And 66 is B, so 01000010, capital B. 111 is lowercase o, so 01110011. And lowercase b is 98, so 01100010. So we can represent now characters as collections of 8 of 8 digits. That's kind of nice. Boolean, another kind of information that we want to represent. We can represent Booleans as true or false, just one bit. You can say 0 is false, 1 is true, or the other way around. Doesn't really matter. So we have some simple data, but how do we represent more complicated things? So for more complicated things, it depends on the language. In Java, we use something called objects. So primitive types in Java are the basic ways you store data. And there's some basic types that we will go over. There are a number of different primitive types, like int for integer numbers, double for double precision floating point decimal numbers, char for single characters, and boolean for true false. Those are the 4 that'll be the primary ones we use for AP Computer Science. So you got to know that there are times we store a lot more complicated data, like a word or a complete sentence instead of a single character, or storing a student name and a GPA together, or storing an image file, right? To do this, we combine multiple primitive types into more complicated structures called objects. So in Java, what we're doing with objects is we'll say like, okay, maybe a student is a kind of object, and that student has a name and a GPA and a student ID number. And the name is a string, which is actually a collection of characters, and the GPA is a double precision floating point primitive type. And the student ID number might be, you might store it as an integer, or if it has letters, it might be stored as a string, which is a collection of chars. But you build those more complicated structures out of the primitive structures. And we're going to spend a lot of time in the first part of the class talking about how data is stored, because it's pretty fundamental to understanding how to write programs. You need to understand how to store data and what's the right way to store data for a particular task. And that's